Okay, so good day everyone. Our topic for today is about tree search algorithm. So in computer science, a search tree is a tree data structure used for locating specific keys from within a set. The search tree algorithm uses the key from the key value pair to define the location, and then the application stores the entire key value pair at that particular location. So what is the best use of tree algorithm? Spanning trees and shortest path trees are used in routers and bridges, respectively, in computer networks as a workflow for composing digital images for visual effects. A tree is a hierarchical data structure defined as collection of nodes. Nodes represent value in nodes are connected by edges. A tree has the following properties. The tree has a node called root. Okay, so please watch, and if you have some question, do not hesitate to post your question in our chat box.
What I'm going to talk about today is basically this tree search algorithm, where we build from a state space this search tree. And the question how to build the search tree is given as a strategy for solving this search problem. And the algorithm is written here in pseudocode. We basically have a function which takes a problem and a list as input, and it returns a solution or failure. Most important notion is this list, this fringe, which contains all the nodes that still need to be explored, so in our search tree. And what we then do is we have an instantiation phase, so we insert the initial state node of the problem to the fringe. And then we look at all the possible successors of this first element in the fringe, which is the only element at the time. If there is no successor for this node, we return failure. If there is a successor, which is a solution, we return this as a solution, and otherwise we have to extend our search tree. And now the question is, how do we extend this search tree? Extending the search tree means adding new nodes to the fringe, and how we do that determines how we search in our search space. And the sort of most simple way of doing this is called the breadth-first search, and that is basically implementing the fringe as a FIFO queue. Who knows what FIFO stands for? First in, first out. Yes. So basically, it's the notion of a queue. In this case, we start from a problem where we have the root node, which is A. We put it in, and that is our first iteration. Then we take it out and we look at the possible successors of A. And these are B and C. And what we do is we add them to our fringe. Yeah. So now the question is, what is the next node to expand? And that is the one that is first in the list. Yeah. And I look at the successors of B, and I add them to the list. Suppose that none of them is a solution. Yeah. And then I take out the next one in the fringe, which is a C. See it here. And you add the successors of F and G. And so on and so on and so on. And basically, by using this data structure of a FIFO, of a queue, you get the behavior that you start with the top, and then you explore the first level, and after that you explore the next first level. Basically, you explore breadth first, the level of the search tree. Yeah. So suppose now we have this simplified Schnapsen version, which is just about, we have a hand of cards, and we want to reach a certain number of points, maybe more than 20, and we have to choose which card to play first in order to get to more than 20 points. And what you basically do is you look at the situation where you played the first card, you look at the situation where you played the second card, the third card, the fourth card, and the fifth card. And basically you put all those 5 states in your fringe, and then you evaluate the next one, and you look at all the 4 combinations that you could have. So this is a jack, I think, yeah, jack, queen, and so you could now play the jack, the queen, the ace, and the king. That gives you 4 more states you can end up with. And in this case, you can stop there because you have found a solution. Then I'm missing one there. So you first would have to explore the one way you have played the jack, then you have to explore the one way you played the queen, and when you have the one way you played the ace, you found a solution. So we now found a solution, a path from the initial state via this decision. I think I even got arrows here. So my path to getting to playing more than 20 points as quickly as possible is found by exploring. I should have taken these 2 as well. And then I find the solution. So basically, if I want to play at least 22 cards to more than 20 points with as little cards as possible, I can just play first this ace and then the second ace, obviously, and then I get to 22 points. It's trivial from a human perspective, of course, because you would always use the highest cards to play out. But for a computer without any additional knowledge, this is not so trivial. It's a sort of a systematic, we found the solution by systematic search.
Question.
Yes?
Can we play it, or will that take too long? Can we play out this scenario on like there?
Sure. So I call the first one A. Yeah, so I don't want to draw them. So I have my top one. I look at which of those, from which state can I get by playing a card out of this hand. And then I get 4 ones. This is where the B would be this one, C is this one, D is this one, E is this one, and F is this one. I forgot one, of course. Yeah? So this one has already gone because I did the exploration. Otherwise I wouldn't have found the BC, the top 5. So now I have this situation, because now I want to explore the B. And the B was these 4 cards. Yeah? So I now have 4 possibilities. I can play the jack. So I can play the jack. I can play, what is it, the queen. I can play the ace, and I can play the king. Yeah? But that gets me to 3 new states. Namely, what would it be? Queen, ace, and king. This one would be jack, ace, and king. This one would be jack, queen, and king. And this one would be jack, queen, and ace. Yes? So then I give the names. So this would be G, H, I, and J. The nodes now. And I would add them to the fridge. G, H, I, J. Yeah? So now, looking at this state, I know that I'm done. It's a solution. Because I've played twice an ace. So this has a value of 22 and is a solution. So I can stop expanding. I don't need to expand the C anymore because I found a solution. suppose now that I would want to find 25 points, so this wasn't a solution, I would have to go on. And that basically would mean I need to take out C. C was this one. Yeah? And then I have the situation that I have, again, the 4 cards. And I would have to do the expansion of all 4. And then I would first play the, what is it then in this hand? If I have an ace, I can play an ace, a queen, an ace, and the king, in order to get me to 4 new situations. And I would have to add them at the end of the cube. Yeah? So it's very simple. It's just the only thing you need to remember is that this data structure always adds the things at the end, and the new things to explore takes from the beginning. And that allows you to explore all the nodes systematically, level by level by level, until you found a solution. And here I'm quite lucky that I found a solution so early that this was a solution just for the sake of making it fit on the board. So now we had the question yesterday, just a quick recap. If I want to explore sort of the 3rd level of the tree to find a solution, and I didn't find a solution earlier as I did here, how many states do I need to explore? How many things do I need to have in my list in the end, in my queue? So I hear 120, and that is 5 factors. Yeah. So this was now the case where we don't take back cards. If you go to the first part of the game, you get your cards back, and then basically instead of having 4 options here, instead of having 4 options, I would have 5 again. So how big would my search space be if I would always refill my cards? 302. Say it again. 3,000. Okay, and that is 5 to the power of 5. This is now if I explore until the end all 5 levels. So if you have to explore to the 3rd level, it would be this number. Yeah? So it is always the branching factor to the power of the depth that you're looking for. In the case that your branching factor remains the same. Here the branching factor, in this case, gets smaller. So the calculation of the number of nodes that you have to explore gets is smaller. Yeah. So why I was asking this obviously is the question, how efficient and how good is an algorithm? That depends on how many of the nodes do you have to explore before you find a solution, and how expensive is that. In this simple case, when you only have 5 cards and very few actions, it doesn't really matter that much. But if you have 10 cards already, we're really getting already into some kind of computational problem. So in order to understand that, we want to look at the complexity of the algorithms of search. So our strategy can be measured in different ways. The first one is completeness. The question is, do I always find a solution if there is one? Yeah, so that's a question of completeness of an algorithm in the search problem. The second one is optionality. Does it always find the best, the least cost solution? So here we haven't defined the notion of cost, that will come later, but for example, you could say the number of cards that are played are my cost, And then you want to find the one that is most up in the tree. The question is, does breadth-first search always find the best one according to the cost of playing the fewest cards? The third thing you want to measure is the time complexity. How long does it take? How many steps do you want? And you don't want to measure that in seconds, but you want to measure it depending on the number of cards or the number of the properties of the game. So in this case, we can measure the complexity of the time that it takes to find a solution by the number of the branching factor. So that's the branching factor B to the power of the depth of finding a solution. So that is the time complexity measure for depth-first search. And I use this O notation, which is this sort of simplification of where you take away all the sort of small prints and the plus ones and the times 5. This is the most important order of magnitude kind of information you have about the algorithm. So that's in terms of time complexity. And now the question is, how much space, how much memory do you use for your algorithm? And in breadth-first search, you have a lot of things that you have to write in the frame. So here we have taken off 3 of the, I don't know how many. But if we go now one level lower, basically it turns out that we have to put in memory almost all of those nodes that we have to visit. You can take off very few as compared to the ones that you have to store. So this is the time complexity. And if you take the space complexity, it's comparable. And I can tell you that for real search problems, this is really deadly. Time is something where you might say, okay, I can wait, and we have very, very efficient machines. But if you look at this table, it's a very simple memory. It has been an experiment for how many nodes do you need to store for a certain tree. I think I don't remember exactly what it was. It was, I think, breadth of 10. And then think of how deep you go in terms of time and in memory. And if you look at sort of the number of nodes that you get in order to calculate, then this was, I think, 10 years ago. So I think we would now calculate this depth 10 with 10 cards with 10 to the power of 10 or 11 nodes. We would be able to do that in a reasonable time. But we would not do that on our laptops with terabytes of data. Even if we would store this very efficiently, there is no chance that we would look at a tree, a search tree of 10, so branching factor of 10, systematically to the end with breadth-first search. So imagine now you implement the same game, a simple, stupid game that I have with the 5 cards where you want to play and you want to check out whether you can find what the values are. This is already becoming computationally impossible because of this part particularly, the space problem. So, therefore, or probably also because it's the logical way of doing things, people have looked into other ways of dealing with research. And there is the depth-first search. And if the one is the breadth-first search, you can already imagine what it does. It goes depth-first, searching for a solution until it reaches the end of the search space. And basically, you do that by a very simple trick, and that is you use a different data structure for your fringe, and that is a queue, or a stack, a LIFO queue, sorry. A LIFO queue, and that is now last in, first out queue, which is also known as a stack, as a data structure. So let's see how that works. We have our data structure is not a queue now, but it is a stack. Yeah? So we start with A. Put it in our stack, and we take it out and expand it. What do we get? We get B and C, so in order to keep with the order on how you put in that is might be confusing, but you can choose in principle how to add them to the fringe. And then the next step is you take the top one. You always take out the top one from this stack. This is B in this case. So now we look at expanding B, and we add E and D. Yeah? You see how this works? We again take out the top of the list and we expand the top. And we add I and H. So we take the top again. The top has no things to explore anymore. Suppose we haven't found a solution yet. Then we take the next one in the list. And that is then the I. The I also does not have anything to expand. So we take it out. Now the top of the list is the E, this node. And we can add new stuff to the stack. So if we expand E, we get, so this one we've done. If we expand E, we get J and K, so we add J and K. And again, we look at J, is it a solution or it's not a solution, and so forth. Yeah? You get the principle? And that basically gives us a way of exploring the tree from the root to the leaves in one go down here. Then it does something that's called backtracking. So if this is not a solution, I have to go to the next one and look right in this case. If this is not a solution, I have to go back, and then the one that is again the best one according to the depth first search. And I do the same. So it's now, once I've explored all the J and the K, the next one in my list. So I see that E cannot be explored anymore, and then the next one in my list is the C, and I do exactly the same. Yeah. So basically, now if we do this with our Schnapsen example, the difference would be here that that at this point we would start exploring this node and not looking at all those, but we would only looking at this first one and would go on until we find a solution that we find in this case. Namely the one where I first played the, what is it? Here I played the jack, so that gives us 13 points. Here I played the queen, that gives us 15 points. And then I play the ace until I'm in this state. And this is a solution, because I've now played 26 points. Yeah? So I find a different solution with a different search strategy. And in terms of cost, I needed now not 2 cards to play out, but I needed 5 cards or 4 cards to play out to get to my 20 points. Yeah? So I haven't explored the tree in its full breadth, but I only explored one way down. Yeah?
Doesn't that give you a solution that might not be the least cost?
Thank you for saying. This is it wasn't a queue, it wasn't discussed beforehand. Indeed, this algorithm is not optimal. So you do not find the shortest path according to the depth of the tree. Yeah, so how many happening here? So that is the answer to the first question. is it complete? Oh no, sorry, the second one. Does it always find the least cost solution? The answer is no. The first one is also interesting. Does it always find a solution if there exists one? You're a very clear yes. So this is my initial state. This is the state A. I do depth first search. So I put the J in my stack, should start down here. And then I start at the A. And now I have two ways to go. I can go to the J, and I can go down to the S. So I put the S and the J in my stack. And I take out the J because I have to expand the J's, and that gets me an A. And I have to expand now the A, and we know that this was the S and the J. So I take out the J. And I think you see what's happening. I'm now building a tree which is J, A, J, A. And if I implement my depth first algorithm this way, where I don't check for duplication, then I might get into an infinite loop. Yeah? So basically depth first search is not complete. Because if you implement it without extra knowledge, it does not always find a solution. Because this algorithm, if I implemented it this way, and the trick is of course that I put those two in a stupid order. I put S again in, and I should not have this one is there. Yeah, I think, yeah. So I should not have put J again in, because I have already explored it. So if you do the duplication check, then you can avoid this. But you need to add extra knowledge. So the pure depth first search is not complete, it's not optimal. What about time complexity? So how many nodes do you have to explore in the worst case? All of them. And how many are they? Okay. So the time complexity is again in the order of the branching factor to the power of the depth where you find the solution. So if you do the breadth first search, you have one advantage, because what you can always find is the restriction that you only have to go to the depth of the first solution. Yeah? Here you might really have to explore the whole depth of the entire tree. Okay, so that is time complexity. What about space complexity? Are you the same? Does it? No, it doesn't. It only remembers the ones. You always have only to remember the ones that you need to explore next. Yeah? Yeah. You need to explore one, I think it's what's the precise number? I'm sorry? Yeah, it's more than just D. It's not linear. It's I think it's B times D. Yeah. So you need to do the depth, and then for the branch, you need to the level that you have explored, you need to keep this. So it's bigger than the linear, but it's still completely different ball game between this and this. Yes, you have a question?
Yeah, if the algorithm is not complete, how can we have a time complexity? Shouldn't that just be, because you said you could get stuck in infinite loop, wouldn't the worst case time complexity then be that infinite loop?
D could be infinite. Good question. So here's the summary of the algorithms. So breadth-first also could be, actually I cheated a little bit. Breadth-first can also be incomplete. I think we didn't even talk about it. So breadth-first could have a problem if you have infinitely many choices to make, and then it's obviously impossible to find the right solution. So if we consider a game that you pick at every move, you pick a number out of the rational numbers or the natural numbers, then I cannot even draw your search tree because I have infinitely many options to choose from. The natural numbers is obviously infinite. So I cannot explore the search space when I have an infinite branching factor. But as soon as I have a finite branching factor, so finite number of options, then my algorithm is complete. Depth first is not complete, and then we have the time, which is more or less the same. So here the D stands for the depth, where the solution can be found, the first solution can be found, and this is, I think, the maximum depth. The space complexity is really the big difference, because if you do depth first, you only need to keep one branch more or less with a little bit of overhead in memory. So that's a big difference. And on Friday, I will show you one of my favorite algorithms that sort of solves the magic of combining both the completeness of breadth-first search and the space complexity of depth-first search. Yeah?
So we started on the slide by tree search.
Yeah.
And the definition of a tree is acyclic graph. So how can we end up with this situation where we have a cycle?
I built a tree out of a state space. So this is my state space. And the tree I built is this. And this is an acyclic graph. So this is the search tree. And this is a search, the state space. That's the difference I tried to explain yesterday at the end of the lecture. Two classical and very simple approaches that you can take, namely look through the tree in a breadth-first way, and that means basically you start with the top node, you look at all the children, systematically all the children, and you check whether they satisfy your goal conditions. And then you look at all the children of your children, and the children of the children of the children in the next level. So you basically build this tree by looking at the breadth of the tree. And I think the data structure that we used for it was a queue. Yeah. So if you use the data structure of a stack, then you do the depth first search, and that basically allows you in some cases to find the solution easier. You have to lessen memory, but there's disadvantages. So these are generic methods, and we want to understand what they mean, what the consequences are of choosing specific methods over others. And the way we did that was to look at, and this is, I think, a very classical computer science approach. You look at generic properties of the algorithms. And these are usually the complexity of time. So how much time does it take to find a solution, or all the solutions, or the best solution, or whatever. It's the complexity in terms of space, memory. So how much memory do I need for my algorithm so that I can solve the problem? Third one is, do I find a solution all the time or not? And is it always the best solution that I find, or do I find the solution in the best possible way? So these are typical properties of analysis of algorithms that computer scientists should make their daily bread. You should understand how complex is my problem, how complex is the algorithm that I use, and you try to find a good match for both. And if we look at the breadth-first implementation of the algorithm of state-space search, then we find that in principle it's a complete algorithm, so we always find the solution. It's an exponential algorithm in terms of time, so it depends on the depth of the solution, but you need to take the full breadth of the tree into account, and that can be depending on the branching factor b and the depth of the solution, and basically the complexity is in the order of b to the power of d plus 1. In terms of time, this is extremely complex. But worse is that this is the same in terms of space. And that basically means that you need to have enormous amounts of nodes that you have to keep in memory. In depth first, this is the same in principle for the time complexity, but the space complexity is better because you only need one branch in memory at the time. The price for this is that you're not complete anymore. So it can happen that you do not find a solution if you have, for example, cycles. So I said this is sort of bad news. And it's in principle, it makes it, on the one hand, we have, of course, the arguments that we can use human information, we can use the heuristics, we can sort of order the state spaces that we visit in a way that is more promising. So we have a problem on the uninformed side, on the one side, but still this is a huge problem, even if we have informed search. I don't know, yeah?
So in terms of depth first, in the first two rounds of phase 2, depth first is usually better. Wouldn't it be optimal to then switch to a depth first after the first 2 rounds?
So this was a very complex question about the application of breadth first and depth first for Schnapsen in phase 2. To which I have to admit that I can't give you an answer in this second. So I will think about it in the break and maybe come back to it and maybe not. So maybe I have to send an email. And another question is, did anybody read my rant in the announcement about complexity and about the combinatorial factors of the game that I sent yesterday night, how complex the game is. Yeah? I'm not sure about the real mathematics, but I think what was clear is that I was heavily underestimating the complexity of Schnapsen, because I think what it turned out was that, if I am correct, that we have in the order of 10 to the power of 18 different nodes that we have to search through. If we really want to optimally find a solution. So basically, if you say we do a depth first, a breadth first search, we need to take, in the worst case, maybe 10 to the power of 18 or 10 to the power of 20 even, I think it was, nodes in memory. You will understand that this won't work. I think there are not that many atoms in the universe. That is the sort of the boundaries we're looking at. It simply is impossible. Whereas if you think of the approach, if you use depth first search, the only thing we have to keep in memory is 20 moves, because we have 20 cards to be played, so there are 10 tricks of 2 cards. So we have a tree of depth 20. This is this n value. So we have a space complexity of only the breadth of the tree times the depth of 20. That's easy for a computer to implement. We have this memory on our daily output. It will take a decade or 2 to get to the solution, but that's a different problem. At least we can run our algorithms. Yeah. So, as I promised you, this was a problem in the 70s, 80s, whatever, that people thought we can't solve this. This is simply impossible. And then they came up with a very, very simple solution that I think is really a great example of how science can how simple science can be and how beautiful it can be if you really come up with a good solution. And the observation that this was based on is that if you look at a tree, and you have a branching factor of, say, 5, yeah? Then on the first level of search, you have 5 options. On the next one, you have 5, this would be 5 to the power of 3, 25. Is that correct? Yes, it's the branching factor by depth. So we have 25. So here we have 5 to the power of 3. This is 125. Is that true? No, it's not true. It is, I think. Yeah. The core point that I want to make here, apart from that I can't really calculate in my head, is that you get here 25 nodes on this level, while you have on the level above, you have only 6 nodes. So basically, we have 4 times as many nodes in the lowest level as opposed to all the nodes that are above. And it gets worse. The lower you go, the more the sum of the top ones is smaller than the only level down there. So basically what people observed was that it does not make that much harm in terms of time consumption if I sort of forget what I've done before. The real harm of looking through all the all the nodes in a tree is looking at all the leaves and not what's above. So what they came up with was the algorithm of depth first iterative deepening. And basically what you do is you limit the search to a certain depth. You say, I only look at 4 steps ahead. That's the first step of the algorithm. The second one comes in a minute. So you say, and on this tree of level 4, I do a depth first search. I know that I can do depth first, and I do the full tree, so that will work. And I can't get into loops because I only do it for a limited depth. So I can't get into an infinite tree, an infinite branch. So the problem with if I cut off the depth of the tree is that I might lose out on a solution that comes the next step or 10 steps further in the depth of the tree. Yeah. So this algorithm, if I do a depth limited search, is not complete, as you can imagine. So the idea is to just iterate until you find a solution over these depth limited search where you do depth first search. So how does it work? Let's see whether I have, no, I don't have it open, so. So suppose we have this kind of tree where G is the goal condition. And there might be more stuff down here. Yeah, so let's keep more stuff down here. Okay. F, G, H, whatever. Yeah? So now we want to find the goal in a sort of a mixture of breadth first, a mixture of going through the levels by purely depth first. So how do we do it? In the first step, we only look at a tree of size 1, depth 1, so 1 level. So what is the result of depth first search for this tree? Hey, we don't find a solution. Okay. We were not successful, but it's good. It was level 0. Now let's look at the subtree of length 1. So now we have the tree A, B, E. So how what does depth first search do on this tree? What is the order of the node execution? Yeah?
Executes A to B and then.
Yeah? And it checks whether there's a solution or not. There is no solution, so okay. Chain. Let's go on. So that was depth 1, that is depth 2. Let's try a tree of depth 3. So that's this tree now. I want to redraw it again. So what's the order of execution of depth first search? Shout, help me. B, C, D, D, F, H. No solution found, yeah? Okay. So, yeah, shame. We throw everything away that we've already done. And now we go one level down again. So now we say, okay, let's now do this tree. So this is 3, this is 4. So what's the order of execution of the depth first search tree? Search is A, B, C, E, D, E, F, J, and we found the solution. Yeah? Okay, so if we had applied breadth first search, we would have done 1, 2, 3, 4, 5, 6, 7, 8, 9 nodes. Yeah? That would have been breadth first search, 9 nodes. If we had done depth first search on the full tree, not the depth first iteration, we would have done 1, 2, 3, 4, 5, 6, 7. Yeah? You're absolutely right. 7, yes. Good point. You would have done 7, unless you would have gone down in the tree far more. And now we've done 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. So you see that the time complexity is rather bad. But each time, and that's the core thing, we only had very few elements in memory. So it can be shown, and I think I get to that in a minute here in the slides. So let me go more systematically back to the slides now. So iterative deepening is a general strategy that you can always apply to find the best depth limit L, because we go systematically, we add a level of the tree one by one. And it works very well with depth first search. So this is the example. We start with a limit of 0. We don't find a solution. We go one level down. We don't find a solution. We go one level down. Always depth first, and that's the key, that you do this depth first with backtracking until you have exhausted the entire tree, and you go down until you find a solution. Then even if this costs you a lot of more search, it is complete unless you have infinite amount of branches, which is a sort of special problem that we don't address here. Yeah? So you basically take care of the problem of these infinite paths that we otherwise could not have avoided. It has a time complexity that is in the same order of that we had with depth first search and breadth first search. So it is more, but it's the same order of magnitude. It's the same order of complexity, and that is very important. So it doesn't add, if you add a number of depth, it is not significantly slower. So if we have a simple depth limited approach, we always complete if the solution is within the depth limit, if we do depth first search. But if it's below, we can't find the solution. We can't guarantee that we find the solution. Whereas iterative deepening will just go on until it finds a solution. And it has all the good properties that you would like from an algorithm. Okay, that was all on depth first search. And this is basically the depth first iterative deepening works because you can show that the amount of nodes that are, when you add another level, that are significantly smaller than the amount of, bigger than the nodes that you have already visited in the level before. Another thing I've ignored so far is that in many of the cases, it's not very clear where you start in your search. So, obviously, if you have a card game, you start with a full deck, given to two players get their cards, and you have to find a solution where one of the players win or not. But there are situations where this is not necessarily so clear. So one of the typical examples is a maze, which you can approach in two different ways. So this example of the maze is that you are in the position C3, and that you want to go to the position D3. So that is your goal position, and that is your starting position. And basically the transitions are, you can move from one step in the maze to some other place in the maze. And so from this C3, you can go to E1, and we have sort of abbreviated here the steps. So this going to E1 is a walk via C2, D2, D1, E1. Yeah. So the transition is not a single move in the maze, but the transition is a path until you hit the wall. So here we have one transition to E1, and the other one is to B4, so it goes over up, and then you have to make a decision. In B4, you can make the decision to go to A4 and to go to C4, that's the two parts, until you have to make a decision again, and so forth. And that gives you this search tree, and all you have to do then is in your depth first or in your breadth first search to go from C3 to D3 via B4, C4, D4, and D3. And that's the solution. But obviously there is nothing sort of that stops you to think of how could I have gotten to my goal from my starting position. When I'm at my goal, what steps would I have to take so that I would get there? So basically, you turn the search direction around. So you start with D3 and you think, okay, from where would I have gotten to D3 efficiently? And that means D4. You have to be in D4, otherwise you can't get to D3. And in D4, you have two options. Then you B4, B4, B3, and so forth. And then you turn around the search direction, and you get another path. Which might solve your problem easier, faster, or not. And to show you the difference between the two, I have a question. The first one is, this only works if you have a clear goal. If there is, the goal is the same, so if you have one goal, or maybe two, one goal, and then you can start from this goal to go to your original position, to a starting position. In chess, for example, you don't have a unique starting position. There are millions and millions of winning chess positions. Same for Schnapsen. There are millions and millions of winning Schnapsen games positions. Yeah? But if you have a unique starting position and a unique goal condition, goal state, then it's something worth considering. And then the question is, which impact has the branching factor? And then the question comes from, if you have information about who's my father, I know my fathers, I know my children, I know the family history of the House of Orange, or Orange, whatever it's called. And then the question you have to answer is Matti Hüntjes a descendant of Willem von Oranje? Something we always wanted to know. Absolutely, I know. I don't have an answer to that, but for the purpose of this, it's quite interesting. So what way do you think the search makes more sense? So, who knows it? What makes more sense?
Starting from the third,
Starting from Matti Hüntjes. Why?
we could check William von Oranje. Three family, but pretty too wide to check for one person. So starting from him, let us check for his parents, his ancestors, check if he is related to William von Oranje.
Okay, so I guess you couldn't have heard the answer, but it is the correct answer. That if you look at Matti Hüntjes and you go up in the search tree from his direction, there are always two ancestors. Yes? Let me summarize the answers so that we can. Whereas if you go into history, the number of children that people had at the time of Willem Oranius through the generations is far bigger than 2. So it's usually 3 or more. So they had 3 or more children. So if you start out from...
Children died usually, so...
Sorry?
But you don't go deep because the children died anyway, so...
Not in the Netherlands, not in this idealized world. No, but it has been, historically, I think, it has been proven that there is a sort of a branching factor of 3 if you go down in this example, and maybe not in the specific case of Willem van Oranje. I'm not aware of this part of Dutch history, I'm afraid. So, are there any Dutch persons in the room? Sorry, just joking. Sorry, you had a point?
Just, it really depends on how far removed you are, which church is better.
Yeah, so I mean, I think you get the general point of argument. We basically have, in history, we have a person, Willem van Oranje, and he has a number of children, and this one dies. Yeah, I don't know who it was. So it would have been great. So basically, we have a branching factor of 3. So basically, if you want to see whether Matti sits somewhere in here, you will have, I don't know how many generations this is removed, 15 generations or something like this probably. So we would have 3 to the power of 15. Whereas if we start, if this is the average, so it's the average branching factor. Whereas if we start from Matti, we can be sure, and there is no discussion about this, that he always will have 2 parents. So that's sort of historically, I think, less disputed. So we have a branching factor of 2. So we basically have a 2 to the power of 15. And if anybody could do me the favor and calculate 2 to the power of 15 and 3 to the power of 15, I'd be obliged, yes?
Actually, it might be more than 2 to the power of x. If it's not an ideal world, and for example, Matti has in certain cases not clearly known parents, but more like prospective parents.
Yes. So if you turn this into an imperfect information gain, then you might be right. But let's not get down into this direction of. I'm sure. Anyway, let us stop this discussion at this point in time. So do I have numbers? What is the first numbers of 3 to the power of 15? Nobody with a calculator in this world, sure, huh? Say it again. 40 million plus, yeah? And 4, sorry. $1.4 million plus, yeah? And this one? 30,000. Okay. So you see that there is a significant difference between looking down from this tree with a branch of 3 and looking up with a branching factor of 2. Yeah? And you can imagine that this takes, it's no time to today's computers. But this is obviously a blink of an eye and it's gone. So, and if you look at more realistic problems, then you will see that this really makes a big difference. And I believe even that I calculated it on 10 generations, and here already you see that it's a difference of more than an order of magnitude difference. And if you can imagine what kind of game we have, or what kind of problems we address in Go or in Schnapsen or these kind of things, then these considerations become incredibly
Okay, so again, the advantage of search trees is their efficient search time given the tree is reasonably balanced, which is to say the leaves at either end are of comparable depths. Various search tree data structures exist, several of which also allow efficient insertion and deletion of elements, which operations then have to maintain tree balance. Search trees are often used to implement an associative array, and the search tree algorithm uses the key from the key value pair to find a location. And then the application stores the entire key value pair in that particular location. So, of course, the common types of tree, we have the binary search tree. This is a node-based data structure where each node contains a key and 2 subtrees, the left and right. So for all nodes, the left subtree's key must be less than the node's key, and the right subtree's key must greater than the node's key. The subtrees must all qualify as binary search trees. The worst case time complexity for searching a binary search tree is the height of the tree, which can be as small as O log n or for a tree with an element. The B-trees or B-trees are generalization of binary search trees in that they can have a variable number of subtrees at each node. While child nodes have a predefined range, they will not necessarily be filled with data, meaning B-trees can potentially waste some space. The advantage is that B-trees do not need to be rebalanced as frequently as other self-balancing trees. Ternary search tree. It is a type of tree that can have 3 nodes, a low child, an equal child, and a high child. Each node is stored as single character, and the tree itself is ordered the same way a binary search tree is, with the exception of a possible third node. Searching a ternary search tree involves passing in a string to test whether any path contains it. And we have the searching for min and max. In a sorted tree, the minimum is located at the node farthest left, while the maximum is located at the node farthest right. And I think that's it. And this is also our reference. And thank you and good morning. Good day, everyone.